We begin our exploration of gravitation by examining the foundational concepts laid down by two remarkable figures in the field of astronomy, Johannes Kepler and Isaac Newton. These pioneers shaped our understanding of the movement of planets. Kepler introduced his three laws of planetary motion, each contributing to our comprehension of celestial dynamics. The first law, known as the law of orbits, states that planets move in ellipses with the Sun at one focus. This revelation challenged the long-standing belief in perfect circular orbits. The second law, or the law of areas, emphasizes that a line drawn between a planet and the Sun sweeps out equal areas during equal intervals of time, indicating that planets move faster when they are closer to the Sun. Lastly, the third law, known as the law of periods, describes the relationship between the time a planet takes to orbit the Sun and its average distance from the Sun, expressed as t squared being proportional to r cubed, where t is the period of revolution and r is the mean distance. This intricate relationship helps us predict planetary movements with remarkable accuracy. Building on Kepler's work, Newton introduced his universal law of gravitation, which states that every object in the universe attracts every other object with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. This law not only explained why planets orbit the Sun but also unified celestial and terrestrial mechanics under one cohesive framework. Newton's insights transformed our understanding of gravity, enabling us to quantify the forces that govern the motion of objects, both on Earth and in space. As we delve deeper into the concept of gravity, we must distinguish between mass and weight, two terms often used interchangeably but with distinct meanings. Mass refers to the amount of matter contained within an object, and remains constant regardless of location. Weight, on the other hand, is the gravitational force acting upon that mass, calculated using the equation W equals mg, where W is weight, m is mass, and g is the acceleration due to gravity. On the surface of Earth, g is approximately 9.8 meters per second squared. This means that as objects fall, they accelerate at this rate. However, it is crucial to note that g varies depending on your location on Earth. For instance, g is slightly stronger at the poles and weaker at the equator. Additionally, as you ascend to higher altitudes or descend into greater depths, g also decreases, reflecting the complex interplay between gravity and distance. Understanding motion under gravity leads us to the concept of free fall. Free fall occurs when an object is influenced only by the force of gravity, with no other forces acting upon it. In a vacuum, where there is no air resistance, a feather and a stone will fall at the same rate, highlighting the uniformity of gravitational acceleration. This fascinating phenomenon illustrates how gravity operates independently of mass, at least in the absence of resistance. When we discuss gravitational potential energy, we refer to the energy an object possesses due to its position in a gravitational field. As an object is raised to a height h from the Earth's surface, its gravitational potential energy increases, reflecting the work done against gravity. Escape velocity is another intriguing aspect of motion under gravity. It is defined as the minimum speed required for an object to break free from the gravitational pull of a planet without the need for further propulsion. For Earth, this escape velocity is approximately 11.2 kilometers per second. Achieving this speed, an object can surpass Earth's gravitational influence and venture into space. Let's take a moment to explore some real-world phenomena that illustrate the principles of gravitation in action. Tides are a perfect example, occurring in cycles of high and low water twice a day. This rhythmic movement is primarily caused by the gravitational pull of the Moon on the Earth's oceans. The interaction between the Earth and the Moon creates a fascinating dance of gravitational forces that shapes the levels of our seas and oceans. Another interesting phenomenon is the sensation of weightlessness experienced by astronauts in space. Contrary to popular belief, weightlessness does not mean that there is no gravity, rather, it occurs because astronauts are in a continuous state of free fall along with their spacecraft. As the spacecraft orbits Earth, it falls toward the planet but also moves forward, creating a unique experience of floating freely instead of feeling the effects of gravitational force as we do on the surface. Now, let's engage in some interactive checkpoints to test your understanding of these concepts. Consider the center of the Earth. What is the value of g at the very center? The answer is 0, as the gravitational forces from all directions cancel each other out. Next, think about what happens when the mass of one object is doubled. What effect does this have on the gravitational force between two objects? The gravitational force also doubles, illustrating the direct relationship between mass and gravitational attraction. Lastly, consider the feather and stone experiment. Why does a feather fall slower than a stone on Earth but at the same speed on the Moon? The answer lies in air resistance, which significantly affects the feather's descent on Earth, while the Moon's lack of atmosphere allows both objects to fall at the same rate, showcasing the fundamental principles of gravity in a vacuum. These interactive questions not only reinforce your understanding of gravitation but also highlight the extraordinary principles governing our universe.